Hey guys, so quick review of everything we covered this week. We've been talking derivatives, and this week we focused a lot on power functions because when we start looking at the derivative of power functions and the limit laws that we learned back in the previous unit, we can actually derive a rule for finding the derivative, and it makes this process a whole lot easier than using limits every single time. So I had you start out by finding the derivative of x squared and the derivative of x third in the lesson that I posted. And through the limits, we found that it was 2x and 3x squared. Here, I'm showing you the same process. We go through and we do the same thing for x to the fourth. So we do I'm doing the x plus h minus f of x method, and we get 4x to the third for its derivative. So if we come over here, we're looking for a pattern. So derivative of x squared is 2x. Derivative of x to the third is 3x squared. The derivative of x to the fourth is 4x to the third. And what we're seeing here is that the power that we start with up here becomes the coefficient, and power on our x is actually reduced by 1 every time we find the derivative. So following that pattern, the derivative for x to the fifth should be 5x to the fourth. And you could easily use the limit definition to prove that. And what this pattern is called is the power rule. And this is what drives us forward from here on out when we talk about derivatives and applications of derivatives, because we're finding a more sophisticated way to do this by seeing this pattern so that we don't have to spend the work of the limit every single time. We can find the derivative quickly and then use it after that. Now, power rule, when we just deal with power functions, isn't super useful, but we can apply this to other types of functions. So if we look about rational functions, the key here, is there another way to write the rational function as a power function? And something we learned way back in Math 1 is that anytime we had an x in the denominator that had a power, and that does have a power, the power here is 1, we can write that with a negative and not have to write the fraction. And if I look at this rational function as a negative exponent, then I can apply the power rule to it. I can pull the negative 1 down in front and subtract 1 from that negative 1, which makes it negative 2. And then I can just simplify this, clean this up, put that x squared down here in the bottom. That gets rid of its negativity. Negative 1, I end up back with the fraction, which is exactly what we would get if we were to go through this and use the limit definition. And I could do this with any rational function that I have. 1 over x to the third. I could do the same thing. I'd write that as x to the negative third, and then I would apply that power rule to it. Radical functions, we can actually do the same thing with. You see it's uncovered here. This can be written as a power of 1/2, and we learned this rule back in Math 2, I believe. So you got to remember that there is a power on this x, and there is a number in this. So we can do this for any radical function. And then once we have an exponent up here, we follow the same process. The 1/2 becomes our coefficient. We subtract 1 from this, and we get negative 1/2. So then we would just clean this up and look at it that way. When we could do this with anything. If we had 3 to the x squared, this would be x to the 2/3, and then we would follow the same process here. And what we're seeing here is that the power rule can be extended from just whole number powers. This means the power rule can be extended to values of n with any real number. Okay, fractions, anything. We can follow the same process. It means that this is actually a very powerful way to find the derivative very quickly without having to deal with our limits. And as we work forward this week, we extended this to, and I don't have the limit laws up here on this slide, but we extended this up to the limit laws that we saw. We remember that if we had a constant multiplication times a function, we could exclude that constant, find the limit without it, and then multiply the constant back in. Well, because the derivative, this symbol right here, is really shorthand notation for our long limit, it means that we can do the same thing here. If we see a constant multiplication, we can pull that out front, take the derivative of just the function, and then multiply the answers when we're done. Same thing if we see two functions added or subtracted. We can take the derivatives of each of them and then add or subtract the answers after we use the power rule on them to find their derivative. Those ones weren't too bad. Now, when we look past that and we had two functions that were being multiplied or divided, we had what was called product rule and the quotient rule. And here up top, I said it might be tempted to think that the derivative of the product of two functions is the product of the derivatives. But unfortunately, that's not right. Same thing with the quotient. It's not just the derivative of f of x divided by the derivative of g of x. We actually need to go through this process. So these are going to be something we have to memorize, the product rule and the quotient rule. So given two functions, we take the first function unaltered, multiply it by the derivative of the second, plus the second function unaltered, divided by the derivative of the first. With the quotient rule, okay, we've got a subtraction on top of this numerator that we'll have to simplify out. But the top part's the hard part to remember. Up here, it doesn't matter which way you do this, because there's an addition. You're going to get the same thing no matter which function you multiply by the derivatives first. But down here, because of the subtraction, I need to make sure that this second one is always second, because if I flip it around, I'm not going to get the right answer. I'm going to be off by a negative. So we look, f of x is our numerator, g of x is our denominator. So when we start this, the first one, it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. And then the bottom, the denominator gets squared. So these are two things that we're going to have to memorize and practice. So I'm going to work through a few problems here because I think that might be why you're watching this video. But our top two up here, these are going to just use our sum and difference rules. This one right here is going to be an example of our product rule, and this one down here is going to be our quotient rule. So let's work through these and see what happens. Now, when we talk about notation with this, I'm going to be very disciplined with this, and I suggest you do as well. So we want to take the derivative of all of this thing, okay? Now, 12 is a constant, so by that derivative, or by the limit laws, I know that that constant I don't need to work with the derivative of that, but I do need to find the derivative of that x to the 7th. Now, because these are being added, I can just take the derivative of this one and add them afterwards. So I'm going to pull the constant out in front of that one, take my derivative of x to the 5th, just the power function. I'm going to follow suit. Same thing with my next term. And same thing with the last one. Now, there's no x with this one, so we need to remember this. We do need to take the derivative of the 9 here. But what happens when we take the derivative of 9? Derivatives of all constants are 0, so that constant actually isn't going to matter. It's going to disappear. So let's work through this. So we're going to have 12 times 7 comes down, 7 minus 1 is 6, plus 4 times 5 comes down, minus 1 from the 5, and we get 4. 3, the 2 comes down, we get 1 right here. And remember, this turned into 0, so it's going to disappear. And then from here, all we need to do is just multiply this out and clean it up a little bit. So 12 times 7 is going to give us 84, x to the 6th. And 4 times 5 is 20, x to the 4th. And negative 3 times 2 is negative 6. And that's going to be x. And this is our derivative. We can ignore the constants when we take the derivative inside here when we have other variables to powers, and work our way through it and simplify. We're going to do the same thing right here, but I'm going to rewrite it first. So this is 30, and this is x to the 1/2 plus 7, and this is x to the 3/7. So first thing you want to do when you see a radical is you want to rewrite those things as fractional exponents. Now we can follow the same pattern that we did up here. Write the constant out front, we want to take the derivative with respect to x of x to the 1/2, and then the derivative of x to the 3/7. So that's going to yield us 30 times 1/2 x. 1/2 minus 1 is negative 1/2. And that's going to be 7 times 3/7. And when we subtract here, we're going to get negative 4/7. And now we just need to simplify that. So 30 times 1/2 gives us 15. Now we know that this x to the negative 1/2 means this thing's going to be in the bottom. So that's going to simplify to 15 over x to the 1/2. And to that we're going to add. So 7 over 1 times 3 over 7 is going to give us 3. Remember, this gets pushed into the denominator to get rid of its negativity now. So that's x to the 4/7. And the only thing you want to be careful with is sometimes your answers for these won't be written with those fractions. It's going to be written with the root symbol. So this is the square root down here. And this is 3 on the top, the 7th root of x to the 4th. And there's our derivative for number 2. Now working on to number 3. Now we could multiply this out and then just use the difference rule on it. But let's practice the product rule here. So for this, we are going to take the first function and multiply it by the derivative of the second. So we're going to go 7x squared, and we're going to multiply that by the derivative of 5x to the 3rd minus 4x. And then we're going to take the second function, that 5x to the 3rd minus 4x, and we're going to multiply it by the derivative of first function. This one, the order you put them in doesn't matter because we're adding these things. So you're going to end up with the same thing every time. So we're going to have 7x squared, and we're going to multiply that by. Now here, remember, we're going to actually end up using the difference rule right here. This is 5d dx of x to the 3rd minus 4d dx of x. So this is going to be 3 times 5, which is 15. We're going to get x squared, and it's going to be minus, this is a 1, so that 1 multiplies that, you get negative 4, but then that gives us x to the 0, which is 1. So that is the derivative there. And we're going to multiply that by 5x to the 3rd minus 4x. I'm sorry, we're going to add to that this 5x to the 3rd minus 4x times the derivative here. So remember, the 7 is going to come out front. The derivative of x squared, so we're going to pull the 2 down, and we're going to get 2 times 7, which is 14. And that's going to give us 1, so that's x. And then from here, we just need to clean this up. So we're going to distribute this and combine like terms. So I apologize, that's not 7. So 7 times 15 is going to give us 105. X squared is x to the 4th. And then we're going to get minus 28 x squared. And then we're going to distribute this 14x to both of these. So we get 5 times 14, which is going to give us 70. So that's going to be plus 70. And that's x to the 1st and and x to the 3rd. So that's going to give us an x to the 4th. And then 14 times 4 is 56, and it's going to be negative. And we're going to have x squared. So we actually get some stuff that combines here. So we're going to get 105 plus 70, so that's 175 x to the 4th, and both of these things are negative. So that is 84. So that's going to be minus 84 x squared. So this is our derivative using the product rule. Now we could have, at this point, because this one's easy, we could have distributed up here for this problem. And we would have ended up with what we would need to find this. 7 times 5 would have given us 35, and we'd have x to the 5th. 7 times 4 is 28, and we would have had x to the 3rd. If we found the derivative of that, we would end up with the same thing right here, okay? But sometimes that simplification of multiplying through isn't worth the trouble, especially if you have more than one term in one of these functions, meaning if both of them, if I had something along the lines of this, it would take me longer to deal with that than it would to run through the product rule. So sometimes you've got to pick and choose which way you want to attack this. There's nothing wrong with doing this way. I just wanted to demonstrate our product rules we went through, and I wanted to make sure it was simple enough that we focused on the mechanics of it and less of the algebra. Let's do number 4. Number 4 was our quotient rule, okay? So with your quotient rule, when we find our derivative, most of the work happens in the numerator. So we're going to get the denominator times the derivative of the numerator minus, and I like to put big brackets around this so I don't forget that I need to change the sign of everything in there. This is going to be the numerator, which is 2x squared plus 5x, and we're going to multiply that by the derivative of the denominator. And then the denominator gets squared. So we can just write 3x minus 1, and we're going to square it. So most of the work for this is going to happen up here. I always say simplify this thing first off to the side so you don't have to continue to write a fraction, and it might make life a little bit easier when you deal with the quotient rule. So we need to find the derivatives inside here and then multiply. So that's going to be 3x minus 1 times, if we take the derivative of this, we're going to get 4x plus 5. And then that, when we multiply it out, because we'll need to simplify everything on the top, so we're going to get 12x squared, and we're going to get 3 times 5, so that's 15 minus 4. So 15 minus 4 is 11. So we're going to get plus 11x, and then negative 1 times positive 5 gives us negative 5. Now we need to do the second part here. So this is going to be 2x squared plus 5x times the derivative of 3x minus 1. So the minus 1 is going to turn into 0, and the 1 will come down, so this is just a 3. So we're going to multiply everything by 3, and we get 6x squared plus 15x. So these are our two parts on the top. And then we just need to combine them. But what we need to remember is this is going to be 12x squared plus 11x minus 5 minus all of this stuff. So we'll have to change those signs in here. So that's 12x squared plus 11x minus 5 minus 6x squared minus 15x, and we'll simplify here. So this turns into 6x squared, and we're going to have 11x and 15, so that's going to be minus 4x, and now we get negative 5. So through all that work off the side, the numerator of this thing turns into 6x squared minus 4x minus 5, and we're going to have it divided by 3x minus 1 squared. Now we do need to try to factor this thing, so we need to look, are there factors of 30? Oops. Apologize about that. Are there factors of 30 that have a difference of negative 4? So we have what? We have 1 and 30, 2 and 15, 3 and 10, another with 4, 5 and 6. But if you go and you look at those subtractions, none of those are going to equal negative 4 no matter which way we subtract them. So that's not going to factor on top, and you just really need to check it to make sure that it doesn't factor, because you got to see if there's a 3x minus 1 in there to simplify the answer, but there's not. So we're done with that one. One last topic. So I say if the derivative was x squared minus 4x, then what was the original function? And what we're working with here is what's called the antiderivative, which is something we talk about after we get much further through the derivative, but just the idea of working backwards just to start that process. So the derivative we found was this. What I want to know is, what did we start with? So when we go this way, remember our rule was nx to the n minus 1. Well, if I want to go this way, I need to take my powers and I need to add 1 to them, but whatever this number was in front also needs to be divided by n. The new n, I'm sorry, the n plus 1. So when we do this, we're going to have powers of 3 and 2. Because this one was a 1 and this one was 2, so they're going to get one bigger. And this 8 is going to get divided by 3, so we'll just write it as 8/3 because it's nothing nice. But -4 gets divided by this 2. -4 divided by 2 is -2. So that's one thing that could have given us that derivative. But when we work backwards and you talk about where we started, we actually need to account for something. I could have something here that could have disappeared when I took the derivative, because if this was a constant, when I found the derivative of that constant, it would have disappeared. And the way that you would write that in your answer is you would say, well, that's 8/3 x to the third minus 2x squared. And you just put some capital C here, meaning that when I go backwards, I could have a constant here, any number, something could have an x in it as well. But there's some constant here that will disappear. I'm sorry, not an x with it, just a number. Any real number. Because when you take the derivative of a real number, you're going to get 0. And that's what could have been up here, and we need to account for it when working backwards. Not something we really need to worry about, but we'll talk about working backwards as we work through the derivative each time. So I hope that was helpful for you. Reach out, let me know what you guys need.